I'm just going to give you a few teasers. Going to talk about the 30-meter telescope. Looks real in this picture. I can't wait for it. Wait to see a real picture of TMT like this. This is the summit of Mount Hamilton at the bottom, and the wonderful Keck telescopes in Mauna Kea. You know, expensive telescopes, so we put them on top of a volcano in. So here's TMT. It's also going to go on top of that same volcano. It has a similar principle. The design principle is very similar to that of Keck. It's a segmented design. The segments are smaller than the Keck segments. The Keck segments, as Don said, are about 2 meters across. These segments on TMT are expected to be about 1.5, 1.4, if I remember correctly, the size of the segments, but about 500 of them, as opposed to 36 on Keck. The increase in complexity is really difficult to grasp. I'm going to point out just one aspect of 36 segments versus 500. On the Keck telescope, there are 36 segments, but there are really 6 types of segments. If you think about the symmetry of the problem, the inner ring, you know, there's a ring of segments right in there. They're all identical. You know, there's one spare, there's a 7th segment, so that gets polished while the other 6 are on the mirror, and then you switch that one in and polish one of the other ones that's been on the mirror, and so on. In the middle ring, there are 2 flavors, and in the outermost ring, there are 3 flavors. So there's 6 types of segments. I don't remember exactly how many types. Do you, Don, in the 492? No, but it goes into... it may be higher than that because of the multiplicity of the thing, but it's the number of segments, keeping up with them, the complexity of this is tremendous. It's 9 times the collecting area of the 10-meter telescope, because the area of a circle goes as the square of its diameter. The Hubble telescope, if it was shown on this picture, would be half the diameter of this telescope. This is the Palomar 5-meter. The Hubble telescope is 2.4 meters in diameter. You'd have to scale that up by a factor of 12 to get to the diameter of the TMT. So there's a factor of 12 in each of X and Y by which the TMT should be able to see greater detail than the Hubble telescope. As you know, the Hubble telescope's been a huge hit, and it's the level of detail it can see that's been a huge hit. One of the things that I can talk to you about offline is we recently measured the motion of the Andromeda galaxy across our field of view, up and down and across, not to and fro. To and fro has been known for 100 years. We measured it moving across. The precision it takes corresponds exactly to hair growth on the surface of the moon. I'm not exaggerating. You can see hair grow on the surface of the moon if you're given a 5-year baseline with Hubble. And so you can imagine if you do 12 times better than that, you can do the same thing 12 times further out. Here is the summit of Mauna Kea. It's becoming a really busy place. And this is relevant for the political issue of putting another big telescope on the mountain. You see the 2 Keck telescopes there. They actually are not the biggest domes on the mountain. They're the biggest telescopes. And that's because as we build bigger and bigger telescopes, the technology is getting to the point where you can make the telescope mirrors more curved, so the focal lengths get shorter and shorter. The telescopes get stubbier and stubbier as they get bigger. If you go to the opposite extreme, Mount Hamilton has a 1-meter telescope that's very, very long because it has a long focal length. So this is where TMT will be. It'll actually be hidden from sea level. So this is part of the political sensitivity of not corrupting the sacred mountaintop with another man-made gadget. TMT's light gathering power and high spatial resolution will lead us into very many exciting areas. Just 4 of these are listed here. Looking at early star formation in the universe. I'll talk in a minute about why early is important. Looking at the assembly and evolution of galaxies, looking at planets, really understanding planets in detail, and understanding the fabric of our cosmos itself, the dark matter and dark energy that make our universe behave the way it does. You may notice this circle over here highlighting a particular galaxy. This image was taken with the Hubble Space Telescope. This is what TMT will let you do to that galaxy. All right. This is a simulated image, naturally. We don't have TMT in hand yet, but this is the level of increase in spatial detail that TMT will give us. This particular picture was put together by the WMAP team. Talks about how far back in time you can go. This is a timeline on the x-axis, with the Big Bang on the left, the present day on the right, and it's been about 14 billion years since the Big Bang. But we'll be able to look back out in space, back in time, to some very interesting epochs in the universe's history, to the early development of galaxies and planets, to the dark ages before galaxies and stars existed. Just to give you an analogy, this is it's using telescopes as time machines. If you look close to us, you're looking at really old things. The oldest things in the universe today are very old because they've had up to 14 billion years to age. If you look a little further out in space, you're looking a bit further back in time, and the oldest things are not quite as old. I had the wonderful privilege of meeting this person face to face for all of 30 seconds. And then if you look back even further, you can look halfway back to the Big Bang. And we can see infant galaxies. And one of the amazing things, and this has got nothing to do with TMT or optical telescopes, but what sets the context for these sorts of studies is the ability to see unborn galaxies. This is an ultrasound picture, and I don't know how the doctor decided this was a foot. Medicine makes astronomy look like an exact science, but what it's pointing to are these these blue and green ripples in this section of the picture. These are the ripples in the fabric of the universe. The afterglow from the Big Bang bears testimony to the fact that the universe was not smooth shortly after the Big Bang, 300,000 years after the Big Bang. That's been measured, so that sets the starting conditions for how the universe would have evolved due to the gravity of dark matter and the influence of dark energy. Extremely important to have that anchor there. All right. Just to give you an idea, the 30-meter telescope will allow us to look back in time. It will allow us to see detail, but it will also allow us to make very precise measurements. This very messy-looking plot on the right, it's really talking about what you can learn about the chemical composition of the atmospheres of planets around other stars. So that's a huge step forward in our attempts to march through the Drake equation and approach our origins, trying to understand our origins in the context of the universe. Here's a picture of the galaxies we can see detail with today with current technology, and I'm going to highlight, maybe hard to see with this level of lighting, some of the fainter, more distant galaxies that TMT will give us detail on. You can see some of them circled in red there. Oops, just go back for a second. So just to give you a bit of a timeline, there's a shocking price tag associated with TMT, perhaps not shocking compared to space-based facilities. We've made a start in that direction. Something like TMT is too expensive for a single country's astronomy budget. This is looking very clear, looking at NSF. This TMT now involves an international collaboration. Acura, not the car manufacturer, but the Association of Canadian Universities for Research in Astronomy, represent Canada. They are a member of the TMT Corporation. Japan, NAOJ, the National Astronomical Observatory of Japan. China and India have all selected TMT over our competition, and we're trying to raise the remaining capital for it. The total price tag, by the way, will be twice that. This is the capital cost of construction. Operations for 20 years will be another $1 billion. There was a long and complex process, but it led to something meaningful, led to the selection of Mauna Kea as a site for this wonderful instrument. I want to spend just a couple of minutes now on what TMT means to me and my place in the cosmos, what it might mean to you, your place in the cosmos. So I start with a picture of my daughter when she was a few years old and my son next to her on the left. They are connected by the fact that these entities are made of protein molecules, nucleic acids. They're made of complex molecules. To have complex molecules, you need heavy elements. You need elements like carbon, nitrogen, oxygen. But we don't need to look very far to find these elements. We can look at our planet and our star, and we see these elements are present in abundance. There's oxygen in the air you're breathing, nitrogen in the air you're breathing, carbon. At your latest barbecue, you had an encounter with carbon. These elements, it turns out, were not produced in the sun. So the Earth should have no business owning them. The sun should have no business owning them. These elements were actually synthesized in other stars, ancestors of the sun. The massive versions of these are very good at cooking up these elements, and they're also very generous in exploding at the ends of their lives and returning these elements to surrounding space. So if our sun were born isolated from other stars, not in a galaxy, isolated from other stars, we'd be made of hydrogen and helium today. We're made of stardust, and we owe that fact to the fact that we're part of a family of stars, and a family of stars is what we call a galaxy. I like this particular galaxy. This is the Andromeda Galaxy, and we're in no special place in the Milky Way galaxy. If this were the Milky Way, we'd be there. Not in downtown Santa Cruz, not off in Gilroy. We're in, somewhere like the UCSC campus, somewhere not so special. So in more scientific terms, this is an exploding star in a galaxy. Don talked about automated telescopes on Lick. This particular spot of light didn't exist the night before. This is literally an exploding star caught in the act. If you give it about 1,000 years, it spreads all the goodies that cooked within it, these heavy elements like carbon, nitrogen, oxygen. It spreads it throughout surrounding space. That gets to pollute, or enrich in this case, surrounding interstellar gas. Out of that, new stars are born, and they then go through their chemical cycle and explode in their own terms. Now, so this chemical cycle of stars, planets, galaxies, is what TMT is going to shed tremendous light on. I end with one slide. This is something that Sandy gathered. You may see this again this evening. This is a picture taken from a cave in the southwestern United States, looking at our Milky Way galaxy. And what is absolutely poetic about this picture is the rocks are made of some of these heavy elements, but these rocks wouldn't exist if this home were not embedded within a larger home we call the Milky Way galaxy. And that's where I'll stop. Thank you.